So let's see how we did on our problem of the day where we're finding the empirical formula of a hydrate based on data gained from heating up that hydrate, driving off all the water molecules as much as we can, and then weighing the difference. From there, finding molar relationships, and then finally a ratio. So we have some sort of a hydrate of iron 3 nitrate. I just gave it to you in name form. I didn't give you the formula. So the first thing you need to do was figure out the formula of iron 3 nitrate. Well, iron 3 is a positive 3. Every nitrate's a negative 1. So thus we need 3 negative 1s, 3 nitrates to balance the positive 3. And then we have a hydrate. We don't know what it is yet. That's what our work and experimentation is for. So when we are heating up substances, we often do it in a crucible. And so since we're being quantitative here, we need to not forget to factor in the weight of the vessel that your substance is in. In this case, the crucible by itself is 28.65 grams. And I just pour in a sample of iron 3 nitrate. And it's arbitrary really because all samples in theory should produce the same ratioed results. And I just pour some in, and finally the crucible plus our sample is 37.98 grams. And so I can figure out, well, what was the weight of the hydrate by subtracting the weight of the crucible, and that mass turned out to be a 9.33 sample. And this is probably a good practice in general, because very often when we're weighing something out separately and trying to transfer it into a container, a few flakes of that substance may be lost. So why not actually weigh the difference of the crucible before and after? That's going to be a more accurate result realistically. So this is our sample. And then we heat up our convection oven as much as we possibly can. We try to let it heat for a long time. And then finally, we have, after heating, this is our mass of the anhydrous leftover iron 3 nitrate in the crucible. Once again, we subtract out the weight of the crucible to get the mass of the anhydrate. We're making an assumption that enough of the water vapor has been driven off to where we can try doing this molar relationship and ratio exercise to find empirical formula. So we assume that if this was the initial mass of the hydrate, and this is how much the anhydrate is after we've heated off all of the water vapor, what was the water in a solid form with iron 3 hydroxide and turned into a gas, then that much gas got driven out of the substance. So from there, we assume these two masses. This is the anhydrous iron 3 nitrate. This is the water vapor that we heated off. We divide each by its molar mass. The molar mass of anhydrous iron 3 nitrate is 241.86 grams per mole. I could, show you how it is this in a separate molar mass calculation, but it's basically the molar mass of 1 iron, 3 nitrogens, and 9 oxygens times their molar masses and then summed up. Water's molar mass is 18.015 grams per mole, reflecting molar masses of 2 hydrogens and 1 oxygen. And these are our results when we divide our samples by their molar masses. So at this point, we're hoping to get a whole number ratio. So we compare the two products and divide both by the smaller of the two. This is the smaller number, and we get a ratio unrounded of 1 to roughly 8.8. And this may not seem, well, that really isn't totally close to a whole number of 9. If we're at 8.95, we could say it's textbooks. In reality, common high school lab equipment doesn't have that textbook type of accuracy necessarily. This is considered credible if we probably kept the the machine, the oven going for another 2 days, I'm sure we would get an even closer value. But this is close enough, and we can say that for every molecule of iron 3 nitrate in a hydrate form, we're going to have it in this structure with 9 water molecules as the ratio, 9 hydrates to 1 iron 3 nitrate ion, a compound. And so we would call this iron 3 nitrate non-hydrate. The nana being our prefix that means diet. And there we go.